All right.
Oh, cool.
Is it showing up?
You're
Yeah.
on.
Okay, good. All right. Well, here's what I decided to talk about after Ron called, I think Monday or Tuesday this week. I got to thinking about something I read recently about pointing lasers up into the sky and why is it that we can see a green beam with a green laser, but we don't see much of anything with a red laser. Started looking into that a little bit, and it kind of took me off into another trail of laser beam propulsion of spacecraft. So that's where I ended up. So I hope this will be educational and somewhat interesting. Using lasers and sails. Now, when we talk about sails on spacecraft, I think, and to my mind, what I usually thought of in the past was using sunlight to bounce off the sails and use that as a power source for a spacecraft. But using laser beams is a whole different thing. So they made up this term called directed energy. The sun is considered undirected energy, I guess you would say. So we can get a much more impressive impulse out of a laser than we can get from the sun itself. So let's go ahead and get this started. Photons, little chunks of light, are pure energy and they carry momentum, even though they don't have mass. So we can use that momentum. Of course, it doesn't seem like much, as you know. If you're hit by a flashlight, you don't go bouncing backwards. So not a lot of power in those photons, but there is some power in photons because the National Ignition Facility just recently, this made big news. They actually were able to mush a few atoms together and get fusion, which is in the sun is done, the mushing is done by gravity. But we can also do it here on Earth with lasers focused very intensely on one little tiny spot. We can get atoms to fuse and get that power out. And finally, there was a very slight net gain of energy. Actually, not slight, 50%, I think. I think every 2 joules put in, 3 joules came out or something like that, but it doesn't last very long. We're talking, I think, femtoseconds or something like that. So I don't know a whole lot about it, but evidently lasers can pile up enough photons with enough energy to do that job. So directed energy can do work, directed energy being the laser beam. Of course, one of the applications that's being pursued right now very intensely is by the military and particularly the Space Force to see if we can use lasers in space for weapon purposes. We can knock out satellites and things like that, so which could be pretty messy. So I hope they don't get very good at that. This is the application we're going to look at is quite different, though. Surprisingly, a lot of the research is being done up at UCSB here in our neighborhood for spacecraft propulsion. So let's see what this is about. Here's the basic idea. We take a ground-based laser setup and beam energy to a target in space, which would have, as you can see, here's our Earth over here. I assume you can see my cursor. And then we have the dish out in space that can receive the energy. It provides an impulse. These are, there's a little bit of reflected energy, which can add to the impulse as well. And some radiated energy that's probably just wasted energy, doesn't help much. The diameter of the receiver can be quite variable. They can be huge, they can be small. So we'll see there's quite a range in that. But that's the basic idea. There are 2 basic strategies using directed energy on spacecraft. One is the most obvious, photon pressure. We just, as in the last slide, we just blast a beam up into space. We hit a sail of some sort, and the photon pressure will cause it to move. Same basic idea as the solar sails that use the sun as the source. They just bounce photons off. The other strategy is reaction mass systems. So in this case, we use the laser to convert the laser energy into electricity, and then hook it up to an ion propulsion engine, which then basically just shoots, ions of xenon or something like that out the back. That provides the impulse and the push to get the spacecraft moving. One of the strategies will be, instead of ions, just electrons. You just blast them out the back. The mass going out the back end pushes the spacecraft the other direction. So that's a pretty obvious use of the lasers, just as a conversion to electricity, and then using that electricity to fire up charged particles. The other strategy is ablative systems, where basically the laser is focused on some sort of fuel source in the spacecraft, either a condensed phase, which means liquid or solid propellant. It's heated up and blasted out the back of the engine, or a gas phase propellant like hydrogen. I think this is one of the projects that, in particular, that UCSB is working on. You take up a canister of hydrogen of varying sizes, and the laser is used to just heat up the hydrogen and blast the mass out the back end. All right, so those are the two basic strategies, and we're going to look at them in more detail here. So keep those in mind: photon pressure and reaction mass systems. Strategy one, the photon momentum or pressure. This is the big interstellar hope. How do we get to stars? It's possible with this methodology. 20% of c or more is possible. So these are considered relativistic speeds that could possibly be attained. C being the speed of light. 20% of the speed of light, you're going to cover a lot of space. So relativistic speeds, only low mass would be possible with this method. And so we're talking about something like Mike was talking about with wafers being used as photon receptors in cameras. In this case, the wafers could be a whole computer on a chip, basically. We glue one of those into the middle of a sail and hit it with the laser beam. If it's low enough mass, the acceleration can be tremendous on those things, and we can get them moving through space quite rapidly. It's fully scalable. So it's only dependent is how big a sail we can build up there in space and how much energy we can deliver from the ground. They have a pretty big program going up there at UCSB working on this, about 100 students. A lot of them seem to have gaming experience, and they're using that to develop algorithms to control this, the instrumentation that they're developing up there. And I'll show you more about that coming up. They call it the D-STAR program, Directed Energy System for Targeting of Asteroids and Exploration. I'm not sure, I didn't read anything about their asteroid program, so I don't know what they're doing, if they're talking about just blasting them apart or exploring them. I'm not sure. One of their projects is called D-STAR 1. It would be an antenna that's 10 meters on a side. Wait a minute, I think I've got that wrong. This would be the laser, the ground-based laser, 10 meters on a side. And another one, 100 meters on a side, D-STAR 2. These are all, of course, just plans. They're not in operation and won't be for quite a while, I think. D-STAR 3 would be 1,000 meters on a side, and D-STAR 4 would be gigantic, as you can see. This would be an amazing laser array on the ground. Here's kind of a conceptual idea of what we're talking about. This would be the down the lower left. I hope that's showing up on everybody's screen. It's kind of tucked down in the corner, but it's some kind of a pointable. You can see the little motors down here on the bottom, so it's aimable, and it's composed of these cells. The cells would look like this. They're kind of hexagonal arrangements of laser beams. So we're not talking about building one giant laser that shoots into space. I'm not even sure what that would do to our atmosphere. Knowing what my green laser does to the atmosphere, probably not too significant, but it does move molecules around. I think if we had giant lasers pointing out into space, that could be an issue. In this case, though, these are conceivably buildable laser modules, better than just kind of arrayed together to provide all that directed energy and that power. So here's the concept. We've got down here on the ground, we've got a bunch of solar panels. They provide the energy to the laser array, which then shoots it up to the sail. So pretty simple idea. So if we do go with this photon propulsion direct drive kind of an approach, we're talking about wafer scale spacecraft. We're not talking about pushing a big human occupied space capsule out into space. These are very small. Wafer scale spacecraft with a 1 meter laser sail, which could be accelerated to about 26%, according to their calculations, of the speed of light in about 10 minutes. So the impulse doesn't last like for years, like you might think, shooting out, keep pointing at this spacecraft for a long period of time. These are short impulses that get these things up to their speed, and then their momentum just carries them on. So a 10-minute blast with the laser beam gets this thing up to 20% of the speed of light, and then it's on its own. I wasn't able to figure out what the heck this unit is here in this little screen grab that I got. 20 kGoAccel. If anybody has an idea what that could mean, let me know. 20 kilogram something per acceleration, I don't know. A wafer craft could reach Mars in about 30 minutes. Hard to believe. I assume that would mean at optimal distance, not necessarily at the closest point of Earth and Mars. It would probably be, they'd have to calculate the orbits to get that to happen. Wafer craft could pass Voyager in less than 3 days. Let's see, some of you probably know, is it up Voyager out around 50 AU now, I think? And a wafer craft could pass
more like
150, okay. Could pass 1,000 AU in 12 days and reach Alpha Centauri in about 20 years.
Well, I figured out that name for you.
Ah.
It's 20 kilo G's of acceleration.
Oh, good, good.
So you got 20,000 G's, which is pretty high.
Yeah, that's amazing. Yeah, thanks for figuring that out. That looks right. So these little wafer satellites, I'm not sure what kind of powers they will have, but they can definitely be interstellar as well as interplanetary for us. Here's one little model that they've already built up at UCSB. You can see the basic idea of one of the laser cells is to have these individual lasers arrayed in this kind of a manner, so they can control them, turn them on, and put them in phase with each other. It turns out that's a tricky part of it all. Here's what a conceptual idea of what could be done out in space. Instead of just sending one of these guys off on the mission, put a billion of them up there and just blast them all at once and see what happens, I guess. That could be kind of fun. And it'd be exciting to be living on a planet up around Proxima Centauri and seeing this go blasting through your solar system. anyway. So just to summarize this direct drive system, just a photon momentum exchange. There would be no onboard spacecraft fuel, so that can keep it very light. It's the lowest mass system because it doesn't even have an engine on it. Scalable to any payload mass. No other technology known can offer this. So really, the more powerful of a laser we can build, the longer the impulse is applied. There's really not a big limit on the mass eventually, but this is the only known solution to relativistic flight. The other methods we'll look at aren't able to do that. And some of this more technical stuff I didn't pay too much attention to here, but one idea is, how do you stop these things? Suppose you want to send one up to Mars. How do you get it to stop? So eventually, maybe they imagine setting up a ping pong mode where we put more lasers up on Mars or the moon, so we can hit these things from different angles and maybe slow them down, stop them, turn them around. So those are problems for down the line. Now, method 2 is directed energy by indirect drive, in other words, just throwing mass out the back. Using ablated particles. 3 different modes that I discovered here. One is the induced electron ejection from graphene materials or some other material. They just blast electrons off of it and then accelerate them out the back of the spacecraft. That's not a lot of mass, but they can be accelerated really high speeds. And so they can do the math on that, figure it out. Conversion of light to electricity for ion propulsion. So this would be a photovoltaic kind of conversion where the laser beam actually hits solar panels, basically turns it into electricity. And it turns out, we'll see later in another slide, that these solar panels can be specifically tuned for the frequency of light that they are receiving to get them up to about 60% efficiency. And then the third one be conversion of light to heat for mass ejection. This is called laser thermal energy, I guess it is. I think up in Santa Barbara, they're working on hydrogen as a gas to be ejected out the back, or some sort of condensed matter thing, solid fuel or liquid. Here's a little summary of the advantages, disadvantages of this indirect sort of drive. You could use this for larger masses. It's good in the solar system, in other words. So we're not going to go interstellar with this. There are ways already envisioned to stop these things. We can accelerate them out of Earth orbit, but then how do you get them to stop when you? It's like in a sailboat. If the wind's blowing in one direction, you got to figure out how to turn yourself around and stop. It's not easy to do. But by orbital insertion, they're, according to their calculations, at least out to Jupiter, we can just get these spacecraft to just go into orbit and slow them down that way. And then at Mars in particular, do aerobraking to slow them down. So scalable to any mass payload from grams up to 100 tons. Not for relativistic flight or interstellar. And these could be laser tuned photovoltaics with an efficiency of 60% or more, which I think solar panels on our houses get like 20 to 25% efficiency. So tuned photovoltaics can do much better and can drive any ion engine, depending. So the fuel that is taken along could be custom designed for the particular mission that they're looking at. Mars and stop in 45 days. That'll be something. That'll be really important for if we ever start sending people up to Mars, because of course the exposure to the space environment is the most dangerous thing for humans. Even once they get to Mars, they're safer than traveling to Mars as far as exposure to cosmic radiation. So if we can cut the travel time down from 9 months to 45 days, that's a big plus. Now you know these two broad methods, the direct drive and the indirect drive approach. Let's look at some of the broader considerations. The main advantages of is the use and reuse of ground-based lasers. You can blast these things all day long at different spacecraft, and they're reusable, basically. The NASA Starlight program and the Starshot Breakthrough Initiative, which is the wafer scale or star chips kind of a thing that we looked at earlier. 1 to 10 gigawatts per square meter. That's, I think one of the numbers I vaguely remember from my teaching days is sunlight delivers, what is it, 200 or 300 watts per square meter at the surface of Earth, something like that. So these lasers are really exceeding solar power. But of course, we can't build these kind of lasers yet. So there's that. And then using a phased array rather than single lasers, we have to, I don't think we'll ever be building these gigantic single lasers. It's just too expensive and ridiculous. But again, we still don't even have the small modular lasers. Researchers performed calculations to show that even lasers with powers of about 100 kilowatts and array sizes of about 1 meter could power a 1 gram probe at velocities far exceeding the current record with only minutes to hours of laser illumination. So they don't have to be gigantic systems. This would, of course, be a direct drive system. Here's a diagram. We're not going to go into too much detail with this, but these lasers, when they're put into these multi-packs with all the little units to them, they have to be put in phase to give it to generate the most power. So it starts with a seed laser and then splits it up into fibers. So this is showing 3 different fibers going out to these particular sources with phase shifters built in to them so that they can get all tuned up together. So they're providing a unified wavefront as they leave the laser surface. And steering controllers, a little pointing and all that. These things need to be kind of tuned to hit the target properly. And then a phase reference beacon. Notice this. I got to thinking about what that is. That is actually the adaptive optics component of this. We can't be shooting this laser into space through our atmosphere and expect it to go exactly where we want it to go. It's, our atmosphere is going to screw it up just like it does our seeing here on Earth. So they will be sending up the false star or using other adaptive optic techniques to have to retune this millisecond by millisecond, I suppose, to get it to hit the targets that it's aiming at. So that'll be a big part of the algorithm that needs to be solved to make this thing work. There's a few of the things they're building up at UCSB. You can see they're working hard. And this image shows a bunch of little fibers going into these particular modules. And I thought this was kind of an interesting thing to work through. This is for a Mars trip. What we have down here on the bottom is the Earth's surface. And we'll need to use chemical rockets to get the payload and the spacecraft itself up to past Leo, up to MEO. I'm not sure how that's pronounced, but I think it's like middle Earth orbit as opposed to low Earth orbit. Is this middle Earth orbit? I'm not sure. I'd never heard that term before, but I'm sure they just mean it's below geosynchronous orbit, I believe. Yeah, 13,000 kilometers. I think geosynchronous is way farther than that. Anyway, that's where we have to use chemical rockets to get things up to that level. And then we can start shooting them with the phased array laser once it's all assembled in middle Earth orbit. I'll call it that for now. Shoot up the laser. get this thing blasted off to Mars. So it gets into Mars injection orbit, and the laser's still working on it, I guess, at that point. And then I think this arrow, oops, back up here. This arrow is indicating that something that can bring this thing back to Earth so that the spacecraft itself returns to this middle Earth orbit and doesn't need to land again. It's ready for its next mission. Another payload gets sent up to it and it's ready for another use. The payload gets separated at that when it gets to Mars transfer orbit and gets up here to aero capture and either landing or orbital insertion, whichever. So that's kind of the basic program for a Mars project. So final broad considerations, Moon is probably the best place to place lasers for a lot of these programs, especially the interstellar ones. So someday we'll be building these lasers up on the Moon, and that way we don't have to deal with the adaptive optics and a few other problems. Well, I think Lunar boost to the MPO. So that's a bit of a problem. We still have a dependency on chemical rockets. Low mass missions, it's possible, according to one article I read, we can get some of these wafer spacecraft up to high enough orbit with just balloons or drones, where they'll still be in the atmosphere, I guess, a little bit, but then we can use the lasers to boost them. So very little chemical burn would be needed. For most missions, braking is going to be a major consideration. You know, how do you decelerate when the push is always coming from one direction? For Mars, we have aero braking. For Jupiter, we might have orbital insertion in order to slow the spacecraft down. But for other things, there's how do you stop them? Maybe orbit shaping. I don't know. It's hard to say. And once we shoot these things out to the stars, our spacecraft may be just like Comet Oumuamua, just passing through. We won't be able to stop them. They'll just fly right through like our Comet Oumuamua. Oops, that's it. Seems like there was one other consideration. Oh yeah, I guess it didn't get added here, but one other possible interesting spot to go for is 542. Why didn't that show up? 542 AU from Earth is a solar gravitational lensing location. So sometime in the future, we will probably put a spacecraft out at 542 AU, because it can then look back at our sun and do gravitational lensing around the sun to look out into the universe from there. So that's another thing we'll probably use the lasers for. All right, that's all I have. So stop my
Thank you.
share.
All right. Okay.